Thank you so much, and it's a great pleasure to come here. My first time to come to Washington, University of Washington, and I had a big, very nice conversation with many people already. And we did find some synergies of activities, so hopefully you enjoyed the talk. All right, so for many years, we have been working on this line of work. I mean, it's very broad, so you will see. We are very grateful that we have been getting funding from Department of Energy, two big projects. One is the SciDAC. It's really the application, engagement of math side with application side. And last 7 years was this exascale computing project. And I'm very happy to say that we have now, US has 2 exascale computers. Do you know where they are? First quiz. So one is at Oak Ridge National Lab. It's called Frontier. Another one is at Argonne National Lab called Aurora. And this project actually gave us the opportunity, the resources to do a lot of GPU computing, even though it's not the focus of this talk. But a lot of our recent advances are in GPU, multi-GPUs. And I have a lot of collaborators. And in particular, some of them, they were postdocs, started postdoc with us, and then went on to Rice University, for example, and Santa Clara University. All right. So I'm organizing this talk in 2 themes, but at the end, you will see they are actually not separate. They are connected. So one aspect I want to talk about is, which Anne said, dear to her heart, and she actually, it's difficult to speak in front of the expert. So it's about advances in linear algebra, which could improve ML. So nowadays on street, everybody was talking about ML. But what's behind that, we want to see a little bit. And another aspect is ML. Nowadays you can use that to improve linear algebra as well, especially the software. I can show you some of this. Okay, so let's start. I want to use this example to motivate the talk. So maybe you think this is a pretty trivial example, but just bear with me, and then you will see the meat coming after this. So the kernel methods, actually, I was talking to I forgot his name, my dad? Yes. Oh, yes. And he was talking to me about all these kernel methods. I said, oh, you can give this talk. So the kernel method, you probably heard about this. The key is the kernel matrix. And what does this do is really to code the similarity score of 2 data points. So this is used in any data science, right? And your x1, x2, this could be high dimensional. D could be high dimensional data points. It's not just a PDE, 2D, 3D, okay? And then there are a lot of kernels you can use. So the most popular one and the easiest one to understand is Gaussian kernel, which is given by this, the distance of 2 points, then divided, the exponential function. And then nowadays, people can also use a neural network, sigmoid neural network, to use as a kernel. It's another way of encoding the similarity. So keep in mind it's a similarity. But I want to use this very simple example to show you, hopefully you can appreciate the hyperparameter. That's the business, big business in machine learning, tuning the hyperparameter. So this is the Gaussian kernel. And then there's a hyperparameter length scale. So if this length scale is 0.01, the shape is this. If it's bigger, then the shape is that. So that means, suppose your distance of 2 points is at roughly 0.5, then with a smaller length scale, they are not considered correlated. They don't have, their similarity score is 0. But at the same point with a length scale 0.5, then they have similarity score. So that's, people should, appreciate in different application scenarios, they want to use a different length scale to better capture your correlation among data points. But you don't know. That's why you have to do the tuning. That's, people are talking about hyperparameter tuning. But then in neural network, for example, there will be a large number of hyperparameter. So that's about a kernel matrix. And then what can it do is to do the regression, for example. So the regression could be classification of objects, and it could be binary classification or multi-class classification. But essentially, there are two parts for machine learning. Always there's building the model and then prediction. So it's the same thing here as KRR. You have a training process, which is to build the model. So in this case, you have data points already labeled of why you know those answers. And this is your data matrix. And then the training is to find the optimal weights so that you minimize this residual with some regularization. Okay. And so this W will be your model, the best model, given those training sets. And you can see that the matrix surfaced here. So you have write down this algebraic derivation. Your best optimal weights is given by this matrix inversion. Okay, so this D is the feature space. It can be high dimensional. So once you build the model, you do the prediction. So that means you get a new test vector X1. And what you compute is this inner product of your model against your test vector. In the end, it's going to be a one scalar. And then this scalar output, the sign of that tells you the binary classification. But the kernel trick is really to replace this data matrix itself by a kernel. Okay. The idea of this kernel is really intuitively explain this, or it's not intuitively, but the purpose of this is to embed the data points into higher dimensional space, so it's easier to separate. So in this picture, in two-dimensional space, the green and red, they need to be separated by a circle. And it's actually hard to find the circle. But then if you project into three-dimensional, high-dimensional space, you just need to find this hyperplane. It turns out mathematically it's easier to find this hyperplane. So that's the kernel trick part. So you replace the data matrix by a kernel. So then you see that the mathematical operation in there is the matrix. You need to do the matrix inversion. Certainly, our dear friends are Gaussian elimination, or in the symmetric case, Cholesky factorization, and then they have n-cube operation and square memory. So the work we're trying to do is to find ways to improve this KRR efficiency. So one of the ways our group specifically works on is the off-diagonal low-rank representation of this kernel matrix. And another thing is it's more even internal, is use some randomized algorithm to speed up, to find a orthogonal basis in a better way if you think about randomized SVD, this kind of operation. But of course, this is not the only way to do that, and you can use some other techniques. Okay, so let's talk about this off-diagonal low-rank business. And this algebraic formulation is actually motivated, coming from, it can be interpreted in the context of fast multiple method. How many of you have heard fast FMM? Oh, that's good. So that's almost half, more than half. So the fast multiple method is really the particle method. You think about, you want to pairwise interaction to compute them, but some of the far away particles, you can cluster them as one big lump so that you don't need to compute each individually, but more like, there's a notion of near field, you do individual pairwise, far field, you do clustering. And in mathematical term, it's based on the separation of Green's function. So you only need approximation with the R terms here. That's the notion of a rank. But then you put in the matrix term, the near field will be the diagonal part. So you can think about this particle-particle interaction, the matrix, right? So the near field is diagonal, far field is off-diagonal. Then far field, you can do off-diagonal, compression, right? In the matrix term, usually we think about SVD. But in practice, we don't do SVD since it's expensive. So the reason actually we do this off-diagonal is very often for all these kernel matrices, globally, they are not low rank. They are full rank. But off-diagonal, they're low rank. So that's the key, one key observation. And another observation is, if you look at this picture, how much memory does it save just doing this? Can I save by, 10 times? No, I'm not doing by this. Only this, you'd save only half. Right? You only, get rid of half of this. So that's why you have to do hierarchical. So the way, the analysis goes is if you do this multi-level hierarchical way, then you have a geometric decreasing sequence where you sum up together. That's how you get a log term. So then this hierarchical matrices, so it was pioneered actually, more than 25 years ago by Hackbusch and his group from Germany. There's a general H matrix, then H2 matrix, and there are several special cases like Hodler, HSS. And if you look at all of these, you can do some analysis depending on what's the rank, what's the format you're using. So in the end, you actually can do the, put in this form and compute LU factorization, but it's not traditional LU anymore, it's a sparse LU. Then the algorithm complexity will be something like n to the alpha polylog n. And alpha is smaller than 2 usually. So that's the beauty of this. But then there are different formats. So one thing I want to mention is in order to achieve linear complexity, you have to do a little more. So for example, this is 2-level case. So you have top level is SVD, right, U1, and then the second level here, you have U3. But furthermore, if you do the hierarchical basis, suppose you are doing this from bottom level first. You first compute this U3, and then your U1 is actually a combination of U3, U4 combined with a small piece. So this product is your U1, but you represent as a factored form. So that on the picture here, this vector, you see it's smaller than that. That's how the whole thing, then you can do the analysis, it's a linear time. So you have to do this hierarchical and nested basis. Those are kind of keywords. So now the question is, how do you find those spaces? If you do each of these individual SVD, it's in the end, it's not fast. So one of the ways to speed up is to use a randomized algorithm. And randomized sketching, nowadays, it's started picking up. So the idea is actually very, mechanically, it's very simple. It just says that for this matrix A, in order to find the orthogonal basis, then I will create a random matrix. So let's say Gaussian IID of each entry, right? And then I get this sample matrix. So for this sample matrix, you do the QR factorization. Then that basis is a very good approximation of A. So this Q matrix coming from sample matrix. So then you project it. It's a good approximation. So that's the story. And then there's some literature about the error bound, etc. So then putting in the context of HSS, for example, in the hierarchical matrix, and we saw this picture before, but then you can, as you see this hierarchical way, you would have this naturally the tree structure that will give you, at each level, bottom level, you have this, the small basis, and the higher level will be the combination of the children, and the parent will be the combination of children. That's how it goes. Oops. All right. So, HPC is the big part of our work, but I don't have time to go into detail how this parallel implementation is done. But essentially, conceptually, you can think about all these tree structure will give you a nice tool to organize your parallel multiple nodes. So you can say in the beginning I have 100 nodes all working on the root, and then half of them 50-50 speed to each part, and then 25-25 like that. That's how the parallel algorithm goes. Okay. So then the critical question here is in the context of this hierarchical sketching, what we don't want to do individually. So what we do is actually two stages. One is the pre-processing stage. We draw a big sketch using the original A. And then remember, since we are looking at only the off-diagonal part, so you just, from the big sketch, you did more work. You just subtract some of these diagonal contribution. So that's how you get the off-diagonal sketching. And it turns out this pre-processing big sketch is the most time-consuming part. And before I dive into the improvement for that, so I'll show you some of the accuracy and the application of this hierarchical off-diagonal matrix. So this is the application from classification from University of UC Irvine. They have this ML repo. You can get all these different applications. This is a SUSY data set. It has 1,000 samples for this example. The feature space is 8, so it's not low dimensional. And the application here is coming from high energy physics. They want to classify the two types of particles. So it's a binary classification problem. So in this picture, I'm showing you this A bar, A tilde is the HSS representation. And you can see the relative error with 3 different kernels. They are essentially proportional to the tolerance we use for this internal compression. So this is really good news. So that means it's very predictable how the user wants to set the tolerance, right, for the final output, what's the error you want. And the memory saving is significant. So with different compression tolerance, so for example, 10 to the minus 2, we only need less than 20% of the memory after this compression. Okay, so this is something very exciting, is the SUSY dataset, the same thing, and we compare with scikit-learn. Scikit-learn only has a shared memory parallelism, and that's this orange one. So you can see that in the beginning, they use the Cholesky factorization, order n cube, and you can clearly see the algorithm is not scalable. And we have a distributed memory implementation. So this one with the training set as bigger and bigger. I think this one is on, so this one is on more than 1,000 cores. This is only CPU cores. You can see the scalability with the training set increasing, and then we can still try to solve the problem, which is something scikit-learn cannot do because they can only do one node. Okay. So I'll talk a little bit about the software. And I use this machine learning application as motivation, but in fact, this structured matrix package, we started developing about 7-8 years ago. Traditional motivation was coming from PDE, solving PDE and integral equations. So those for the simulation modeling. So it's not for machine learning, but that very pleasantly we discovered, machine learning application can benefit also. And we have different compression format. And one of the format, I didn't show the picture, is a butterfly, which is very good for high frequency Helmholtz equation, which those formats, they don't work very well because their rank becomes very big. But butterfly, because it's using some complementary low rank structure, it's very nice. So then how do you use this to benefit a scikit-learn user? And we have a Python interface. So that means you will write code, using strongpack kernel. So this is a Python interface class. It is derived class from Python, from a scikit-learn, the base, so that you can access their base estimator classification. So all the ML mechanism, you can use scikit-learn, except the factorization, you will use our factorization. and the speed differences from the previous slide. Okay, so I will spend maybe a few minutes about this, how to speed up this sketching. Because sketching, it turns out this pre-processing is more than 50–60% of the time. And I will spend not too much time because I want to get to the second theme. Just to mention this sketching the randomized matrix is actually you can have a very unified framework to explain all this. Although the theory is still not very complete, but there's already a lot of publications. So what we want to do is, previously the result I showed you, this omega is a Gaussian matrix, each entry IID, right? It's still a dense matrix. And then the operation is still like cubic-like, right, of 3 dimensions, depending on the 3 dimensions. So what we're trying to do is to use some structured random matrices. So that's doing a little further than just a Gaussian random matrix. So that's the idea here. And then there are a lot of different structures. So for example, you probably heard about this subsampled Hartmann transform. We can show you. But if you think about all this, the unified framework can all be explained using this Johnson-Lindenstrauss lemma. It's a JL lemma. What does this say is that if you have a set of endpoints in n-dimensional space, in high dimension, and then as long as you have a lower dimension, this small n is bigger than this quantity, then there exists a linear map F from high dimensional to low dimensional. So you can project these high dimensional data points to low dimensional, and it maintains the length. This transformation give you the length, the distance. They will be bounded below and above by this 1 minus 1 plus epsilon. Okay, so that's a very strong, very powerful tool. And then keep in mind your lower dimension has to be big enough. It's related to the number of data points. So that's all intuitively makes sense. Okay. So then this F is a linear operator, but very often we will use a matrix. So you can think about your matrix is drawn from this distribution over this D by N matrix. And then this JL sketching parameter is actually this operator is a parameterized operator, which means you have a parameter N, and D is dimension, delta is the error tolerance, and epsilon is the length preservation tolerance. So all these random matrix, randomized algorithm, the statement is always like this. The probability of length preservation is maintained with a very high probability. Okay, that's the best argument, the statement you can get is always like that. But this implies that it's a good subspace embedding. So then we can look at all these different random matrices. So we already looked at Gaussian, which is a special case, IID, normal distribution. And then this randomized subsampled Hartmann matrix. Hartmann matrix is structured matrix, but it turns out when you do some randomization of D, diagonal matrix entries draw from +1 - 1 uniformly, and the P it sample the D coordinates from N uniform at random. It turns out this product becomes a very powerful random matrix. And the one specific one we look at is the sparse one, sparsity. So that means your omega matrix has a lot of zeros. Okay, so let's take a look at this. And first we look at the error bound, the concentration bound, because you want to, in the JL lemma, it's the vector length is preserved, but in the, matrix transformation, what you want to show is the norm is preserved. So this first theorem is just says that if your JL matrix is parameterized in this way, and then your norm, this sampled matrix will be preserved, upper bound and lower bound by this. So this is very good because in practice you need this kind of error bound to terminate your adaptive sampling scheme. And furthermore, we have a stochastic relationship between the A norm and the sample norm. So then expected value is the same. So this also is very good because in the real application, very often we don't know A. We only know AR. This is the situation when they say matrix-free operation. You only know the sampled matrix, you don't know the original A. So this gives you the tool to assess the error bound. Okay, so in terms of sparsity, this sparse JLT, it just say, I have this matrix in this distribution, and then there's another parameter alpha, which is number of non-zeros per row. And then these non-zero entries are drawn from this distribution with equal probability. So it's 1 over square root of alpha. So for example, if you want every row has only 4 elements, then you draw the distribution from 1 over 2, negative 1 over 2, the integer. So then you can see that your matrix AR can be represented, if you factor out this 1 over square root of alpha, then will be 2 binary matrix. One is a plus matrix, one is minus matrix. There's no floating point you need to represent. So your matrix here, I gave you a simple example, is SJLT 432, and so it's a 4 by 4 matrix, and then it's 1 over alpha is 2, 1 over square root of 2. Each row has only 2 elements, either 1 or negative 1. So that's very nice because when you do the matrix vector multiplication, there's no multiplication. It's only addition subtraction. You save something already. And also in parallel situation, which I don't have time to go into detail, but the operation here, since the R matrix is very sparse, you actually could replicate all these ones over. So you just need to, keep track of, store the location of this negative 1. You don't need to store any matrix. So the benefit is you have less work to do and also less communication. And then theoretically, computational time, this SJLT time is n squared times alpha. And Gaussian sketching, the dense sketching, is n squared times d. Okay, so you save something, but how large is alpha? And this is still very magic. As I said, a lot of this random matrix stuff, it's still error analysis. It's still a lot of open problem. So this is just our experimental experiment, the result to compare to Gaussian sketching to see how large alpha should be. And this picture is a little bit a lot of information, but let's just focus on the first row first. First row of 3 pictures. And here I have each one is a different size of the matrix. It's coming from the frontal matrix of the 3D Poisson equation. And red one is epsilon is 10 to the minus 2, and the green one and the black one is 10 to the minus 6. So here, for each picture, I have Gaussian sketching, first column, and then I have S1, which means alpha is 1. And then I have S8, alpha is 8. So you can see that even by alpha equals to 4, the error is pretty much stable. You don't need to pick larger than 8, you don't get more benefit anymore. So this is really good news. That means the sparsity of this matrix, I can just choose 6 elements of each row, and you save a lot of work. And this similar story, this is telling you about HS's rank. So when you get a 4, it's usually good enough to get a correct rank. Okay, so let's take a look at the parallel performance. And we compare with a Gaussian, right? And as I mentioned, it's less work and no communication. So that's on parallel machine, it's a big deal. So then the sketching time so remember we have a pre-processing and sketching time, and then actually doing the HSS construction. The sketching time is 47 times faster with different processes. I think up to 32 processes, so we have seen 47 times faster compared to Gaussian. And the total construction time is almost 6 times faster. You got the same kind of accuracy. And each individual picture here, p equals to 32, is just to look at the sketching time, the blue one, versus the final construction time. So you can see Gaussian spend most of time in the sketching, but when you do S4 or S8, so it's very little sketching time. It's all construction time. All right. So that's the first part. I think I can transition to the second part, but I want to pause a little if you have any questions, comments. Yes?
What machines are you using to do these?
It's usually it's the at NERSC, National Supercomputer Center. It's one of the DOE supercomputer center, and those experiments are the data I showed you are on CPU, but all our code right now are mostly or not all on GPU also available. Yeah.
A little bit earlier, you had these different choices, like you had the butterfly and the unified HHS.
Yeah.
So, and you mentioned something about like for, I think you said Helmholtz, like butterfly is the better one.
That's right. Yeah.
How do you decide which one to use for a given problem?
Yeah, that's still very difficult. So HSS, I mentioned, it's easier to explain because of this nice regular structure, but it only works, it only maintains a small rank for elliptic problem. You can show that. And then for hyperbolic or some other PDEs, the rank is not small. So it actually cannot be used. But the example I show you for this kernel matrix, it turns out it worked very, very well. So it's good news. And then the reason of this different format, which currently we're working on the H2, the difference, there's a weak admissibility, strong admissibility. So strong admissibility means that you really respect the data, the distance. But weak, HSS, I showed you the picture partition. They are weak, meaning even at the close to the diagonal part, you still try to do compression. That gives you dominant the rank. That's the bad part. Yeah. So the butterfly is, I think Heather, has some experience with butterfly. Is complementary. It goes both row-wise and column-wise. Then they capture, more, do more compression. All right. So let's continue. I'll try to finish like 4:50. Okay, so the second tale, I want to say, hopefully it's also you can appreciate, is how machine learning could help us, to particularly to help a program to run faster. And the idea here is that for a lot of this, especially if you work on linear algebra, dense linear algebra, let's say, there's a closed form formula to tell you what's the block size you should use to get a best performance, even on a parallel machine. There's a parallel runtime analysis counting in the communication. But the problem in practice is this architecture is so complex. And when you run on the real machine, your theoretical prediction just doesn't work. And that's the idea why you need this auto-tuner. It's more like for the practical side. Each program, you can think about a program mathematically as a black box function. And then there are a number of parameters. Depending on the different algorithm, multigrid maybe has 20, and Gaussian elimination maybe has 4. This kind of thing. And then user wants to minimize runtime, memory, and sometimes both. I'll show you some results. This is called a multi-objective optimization. So this is certainly very difficult to do, manually to tune. And another big problem when you work with a big application is each function evaluation, each program, when you run it, it takes sometimes hours or even more. So you don't have too many data points to help you. So that's why this machine learning needs to help. And I'll give you some very simple example, the parallel dense QR factorization. This code is available, the routine is available in ScalarPack. And parallel, so here I have the number of processes is arranged by number of process row and number of process column. So it's a 2D block cyclic layout. So in this 5 by 5 matrix, my number of processes is 6 processes layout by 0, 1, 2, 3, 4 processes. So 2 by 2 processes. And then each, the matrix is partitioned into blocks. So the total dimension is 5, and the row block, column block size is 2. And number of P row is 2. So it altogether is 2 by 2 is 4 processes. And 3 parameters here. I want to tune MB, NB, and NP row. So this typo here. So as I said, there's a closed form formula, and it's written in the user's guide. It says make a block as square as possible and make process grid as square as possible. So that's essentially this picture. The block size is 2 by 2, process is 2 by 2. But then you run the program, run this auto-tuner, then you found that the tuner actually say for size 2000 case, the block size should be 4 by 8. And the process should be, this is for this case is 24 processes. Process grid should be arranged as 2 by 12. It's not 4 by 6. The square should be 4 by 6, right? And for the 10,000 case, the auto-tuner found that it should be arranged as the block size is 1 by 26, and the process arranged as 16 by 192. So there's no way for a human being even to think about why is this best, right? It's dependent on the machine. Okay. So the tool we are using is actually statistical learning framework. It's many years. It's, I don't know, maybe 50 years. Now people say it's machine learning, but it's really based in optimization, and you can see that the point I want to mention is a lot of these are statistics, linear algebra. It's the math behind that. It's nothing tremendously new. It's been there. So what you formulate this problem as a mathematical problem is you want to minimize a function y with some parameter configuration x, and then with some task in the matrix size, for example. And this framework just says that you build this surrogate model, this f, try to approximate this y. And then you just doing some iteration trying to improve your approximation to this function y. Okay, so it's iterator here. And then in the, this box is a surrogate model. This is, you need a clever way to find the next parameter point to do the function evaluation. So that helps you to improve your surrogate model. That's the basic idea. So the cleverness, a lot of cleverness coming from here to update the model with the new data. And then once you get to here, it's just a Bayes rule to, to predict, get your posterior, improve your posterior probability distribution. So this two boxes, it looks very simple, but all the papers, a lot of papers are in each box. So here, surrogate model building, you can use a lot of things, but we use a Gaussian process regression. And you can use a deep GP neural network to do this modeling, to do this. And then even for the search next point, there are a lot of things. So the very popular one is expected improvement. I'll show you the formula, which will become more intuitively. It's called a acquisition function, but there are a lot of different acquisition functions you can use. It's an optimization problem. Okay. So before we dive into some math, I can show you some simple example here. Suppose your y function is a sine function, which you know analytically, you can draw what it is. So this blue one is your true function, and the black one is your surrogate model coming from this Gaussian process. So in the beginning, I did a 5-point evaluation, and the best you can get is this black in this. And there are a lot of uncertainty here. But then this EI function will tell you to do the next function evaluation at point close to 0.4. So after I did the function evaluation, then I get improved black line. And the next point, EI, tells me that you should do 0.5. Then I do a 0.5 evaluation. Then I get improved, etc. So the next is here, so you're getting better. After about 20, or probably slightly less than 20, you get a surrogate is almost as good as the true function. So that's one-dimensional simple case. And this you can generalize to multidimensional and also the multi-vector valued, so which means you can do multitask learning. So this is a good book about that, and for vector valued function, etc. And then if you look at the mathematics behind that, is really every time when you do the Gaussian process, you're trying to approximate this get this surrogate f, which is predict the mean and the covariance of the function, and then you get better. So the model, suppose you have observation function evaluation of S of them, and then you observe S of these values, the true values, then you can update the posterior probability distribution. So the new mean will be updated. It's by this matrix inversion again, and then the new variance will be updated. So if you look at the formula here, the new variance is actually subtracted, so which means your confidence is improved, right? So intuitively, this is understandable. And then the search phase, so the acquisition function I mentioned, but there's usually a trade-off between the exploration, which you probably heard, meaning that exploitation is you have already done a lot of search in local region that you have a knowledge of there. Maybe you want to continue probe there. But exploration, say, you want to do a little bit global, to do a little bit the space that you haven't touched. So that's the trade-off. There are some parameters also, people have to tune that. Then the mathematical equation for this expected improvement, it looks like very mind-boggling. But if you look at the intuitively explanation is, suppose after some certain number of function evaluation, you already know your current best. And then your next point you want to choose is xi star, and the predicted mean is this. You find the difference between this. So what you want to do is maximize this expected improvement, which is given by this quantity. And it's related to the probability density function of your current surrogate model, this difference of the data point compared to your current best, and also related to this cumulative distribution function. So the formula looks a little bit complicated, but intuitively, that's what it's doing. So this is an optimization problem, but it's using the surrogate function, which is a lot simpler to optimize. Okay, so that's the software. A few minutes, I think. So that's the software framework we have, which you can download the code, the GPTune. And on the left side is our tuner code. So you can see that sampling phase to do the model, and then search next one, then coming back to do the sample. And the interface with high performance code will be every time when I need to do a sample, I will do a function evaluation, meaning I'll run this program, one iteration. Your program could be written in MPI, CUDA, or whatever language, Julia or something. I just need your program return me a value, like a runtime or memory usage. Okay. So then we have a number of papers there. You can certainly take a look. So we have a lot of features. We can do multi-objective optimization, and there's a database because a lot of these programs, they need to run very long time. So it's good to save them in the database in the future. When you need some point, you just pick up the value instead of run on the computer. So a lot of nice features, all from practical point of view. So I'll give you 3 examples, and then we quit, we stop. So the first example I want to illustrate is actually very interesting. It's a multi-objective tuning of this sparse direct solver. It's a Gauss elimination and distributed memory. In this code, the parameter space, currently we look at 4 parameters. One is the column permutation, which reduces filling in the LU factor, and the maximum supernode size, and the supernode size of the relaxed supernode, and the number of processor rows. It's, again, two-dimensional process grid. Okay. And we look at 2 objectives. So one is time, one is memory, because sometimes people, they want to have a trade-off. I don't necessarily want the best time while sacrificing memory, since I don't have too much memory. So multi-objective, usually they will give you this Pareto front. So all these black dots here, you can see it's the trade-off between time, horizontal, and memory, vertical. Okay, all these points are good from 2 objective point of view. Okay, and then if you look at it, you just want one objective. So this light green one is the time optimal, if one objective. And this purple one is the memory, the best. The Pareto front is almost there, so it's very good. But if you just download our software, run this matrix with the default setting, it's here. So you can see that time is more than 5 times slower than the time, and the memory is more than, 8 times more memory. So default parameter is not good for your problem. And this is, we run 80 iterations of this Bayesian optimization and 256 MPI processes. So the next example is the big simulation code. This one is solving the MHD equation to build this, simulate this, model this fusion reactor, ITER, which is being built in southern France. The price tag is more than 25 billion. And it's the hardware, the construction is international collaboration with 8 or 9 countries. The US is part of this. And then they have the simulation code. They need to solve this magneto-hydrodynamic equations. It's a very difficult problem, and it's 3-dimensional. So conceptually, it's this donut shape. And the hole is a 3-dimensional MHD equation. Then they use a 2-dimensional plane to do direct solver to precondition the GMRS for the 3 whole dimension, and 5 parameters to tune. So you can see that this is each simulation, each point, it takes several hours on parallel machine. So with the tuning, you get some improvement. So the last example I want to show is what we did recently. It's actually this, we can tune the scientific instrument. This is the accelerator built at Brookhaven National Lab. I'll explain you the picture. So what is this machine? The accelerator machine was coming from the DOE Nuclear Physics Office. And it's the high energy, heavy ion accelerator. The beam source is coming from this called EBIS, electron beam ion source. So this beam source will accelerate the ion particle and get to the collider. Then they will create, the very bright. So in this picture, you can see it's a collision of 30 billion electron beams, the gold beams. Then the detector shape is the star shape. So the critical thing here is that if you see the number of brighter beams, it's related to the luminosity of the accelerator of the collision. the luminosity. And this luminosity is governed by this whole accelerator multiple beams to see how much the particle can come into here to create this collision. And if you, through this process, if you lose some particles, then your intensity will be weaker, then the luminosity will be weaker, will be not so bright. So that's the whole story here. And in here, the critical part is there are several sections of this accelerator. And then there's some operation control place. So one is this injection line here. It needs to be very high intensity. And then the extraction line here also has to be very high intensity. And then here, there are 10 parameters. So the parameters here in the machine is really the control knobs. And then here, there are 9 parameters, the 9 control knobs. So the operation of this is human being, a person will sit in the computer room, and in the code, they will set these parameters in whatever way, and then start the experiment. Particle will go to the collider to create this kind of collision effect. And the thing is, for these parameters, it's very difficult for a human being to say what's the best, these turn knobs to set. And then what we do is we use this auto-tuner, which we say we just try because this auto-tuner was meant to tune the program. It's not really for physical any machine. So we just say use this Python code, build a Python interface to their control code. And then every time we run through this iteration, then you will change the parameter based on what GPTune tells you should set, based on the luminosity measurement from the machine. And it turns out, the picture is a bit messy here. It's a different section of the optimization. The green one is this injection part, and the blue one is the extraction part, the lower here. But if you look at the table, it's probably more clear. So this is the extraction part, the injection part. And then if you can optimize just one of them, each one individually, you get the gain of this 50% here and 8% there. But you can optimize them together. You will get an improvement. It's even better. So together, meaning you will have 19 parameters, but separately, we'll have 10 or 9. So this is very, the physicists, they are, very happy, say this machine learning really help us in the experimental setting, not just say running the parallel program and modeling. So that's the case, nowadays all these algorithms can be used, not just for traditional modeling simulation code. So that's very exciting. So I will end with the summary here. So as you see that the improvement we have achieved, mostly it's coming from structured matrices, low-rank structure, and randomized structured matrices. Then traditionally, it's helping modeling simulation. Now it can help machine learning. And the parallelism, I didn't dive into detail, but I did mention that very often we use the tree structure to do the coarse-level parallelism. But then if you have a dense submatrices, then you can do fine-grained parallelism, which is a lot of well-known technique. And most of our solvers are algebraic, meaning it's applicable to many applications. But of course, which I didn't talk about, is for some applications, if we have geometrical information, we can do much better than just purely algebraic. This is always the case. So randomization is a big deal, and people started picking up a lot, even in real applications. But I think there are a lot of open problems in terms of understanding the outcome of your calculation, the error analysis, etc. So thank you very much.
Other questions?
Thanks so much. Very interesting.
Thank you.
So for the last example you showed,
Yeah.
Have you also considered maybe training a surrogate model for the
That's right. Yeah,
But you could
yeah.
also, if you're getting enough data, you could also give the surrogate for the machine. So you don't have to even ping the machine, just like run that surrogate.
That's an excellent question. And the truth is that their modeling code is not very faithful. So they do have code. So that's why people talking about nowadays talking about digital twins. You probably heard this. This digital twin has to be very accurate. Otherwise, you cannot use that. So in the beginning, we didn't do we were looking at some code, but it doesn't, it doesn't work very well. Yes.
I was wondering if there is any sense in which the Gaussian process tuning models might generalize from one algorithm to the next, sort of like the concept of a foundation model in the other GPT, other interpretation of GPT. By which I mean, for example, if you would train this tuner on one set of algorithms, if that would provide a good warm start for parameters, for a sort of parameter optimization on another. Does that make any sense?
I think if I understand your question, let's see whether I understand. Is so we're running this training for one situation. Is one function. The surface may look like this, right? But your question is how much we can use this information for another function with very different surface.
Right, and indeed, it'll be hopeless in general, but I guess it seems to me. But I just wonder, within the class of algorithms that you're trying to optimize, linear algebra algorithms, if there's enough sort of mysterious commonality between how parameters enter from one algorithm to the next, that you would have a sort of big set of pre-trained models that would be more efficient in terms of rapidly figuring out how to use the next algorithm, how to optimize parameters for the next algorithm down the line. Sort of like how people do this, literally chat GPT stuff.
Right.
You just train on a big generic thing, and then you just do fine tuning and you solve all language relevant problems.
Yeah, so that can be it's you can think about this as transfer learning.
Indeed.
Yeah, so you can use, for example, I showed you the QR example. You can use that as a starting point for LU.
Wow, how cool.
Yeah, but then this is your starting point. You get a very good starting point. Then your basing, you can probably run fewer iterations. Yep. Yep.
So I'm curious, I used Bayesian optimization for research, and I used BowTorch. I'm curious if you're interested in that.
PyTorch, yes.
BowTorch.
IFBO, yes.
Yeah, so it's by the same people who made PyTorch, and so they're
Right.
maintained by Meta. And I'm curious if, what is the comparison between your package that you maintain and the BowTorch package? Like, what benefits does your package provide, I guess?
So actually, recently our group was looking at a BowTorch, but we haven't done serious comparison. I cannot say too much about it. Yeah.
Okay.
Yeah. But we do have we know about that, so that's good. Thank you for bringing up. Yeah.
Any other questions? If not, then thank you again.
Thank you. Yeah.